Hello. So, welcome to the last week of this course. Let me make the announcement right in the beginning that this portion, this week's topic is excluded from the final examination, but then yes, you still have to do the assignment. Okay, fine. The purpose of this week's topic, especially when we had focused on the Lagrangian dynamics throughout the course, but we focused on the particle dynamics, okay, where we can actually count the number of particles in the system and the finite number of those particles, and we track the trajectory of this entire system in 2n dimensional space if there are n degrees of freedom. Okay. Now, what we are going to do is take this to a system which is called as a continuous system. Now, what do I mean by the continuous system? Look, when you have, for example, a solid, typically we treat a solid as a rigid body, but you see the constituent particles inside the solid body, they are not stationary, or they are not the constraints which we thought of, constraint we talked about rigid body, which is the distance between two particles remaining constant. That is not true. There is always motion of these particles about their equilibrium position, and that constitutes waves in the solids. Now, think of this system which is a bulk system, as I call it, and it has very large number of particles, and probably we may not even be able to solve its number of particles if of the order of Avogadro's numbers. So, we probably will not even be able to solve this system. What we might want to do is look at its bulk features. That means, what happens to this system as a whole rather than tracking individual particles there. And that is when we make a approximation saying that this is a continuous system. So, we do not talk about particles anymore. So, this is the idea of the continuum system. So, the examples would be, so basically continuum mechanics is where you have large number of particles and we are not interested in individual particles motion. So, then we look at the average, some sort of a average quantity on this system. Now, the continuum mechanics includes typically solid mechanics and fluid mechanics. The distinction is very clear. Solid mechanics pertains to solids, fluid mechanics is where you talk about either gases or liquids. And then in solid mechanics, there could be possibly two varieties. The elasticity is when you compress a solid and let go, then it regains its shape back. Plasticity is where the changes are permanent. So, in fluid mechanics, for example, you talk about Newtonian fluids or non-Newtonian fluids and all that. So, there are lots of examples of these. Now, what we are going to do here is, so within the body of that bulk continuous material, at each point I am going to assign a displacement vector, which tells you how much displacement has occurred near that point of the material particles. Okay, this is the idea. In case of fluid dynamics, what you would do, you see, if you take a particular point, the particles would be moving in and out of this volume. So, what you do? You can still talk about density at that point and the fluid flow or flow rate at that point. So, we can assign quantities to each point and look at what happens to these quantities, like how density varies from point to point and how flow rate varies from point to point. So, this is what will constitute, and typical everyday experience of these phenomena is, for example, sound waves. Sound waves are the density waves in the air, something like that. So, this is what we are going to look at. But once we go to this continuum mechanics, will our particle Lagrangian dynamics will work? Well, it turns out that I will be able to generalize this Lagrangian mechanics and also Hamiltonian and Poisson bracket formulation to these systems. Of course, the principles are same, but probably the way in which we handle various quantities there, like variables would be replaced by fields and so on. That of course will be different, but otherwise the principles remain same. Okay. So, this week's focus of course is all about understanding. See, we are not going to do everything about the continuum systems. I am just going to introduce the ideas, the basic ideas and the mechanics behind it. See, the dynamics behind it in terms of Lagrangian formulation, Hamilton's principle and Poisson-Bracket formulation, this is what we are interested in. Okay. And it is a very short time, so it will be just a very basic introduction there. But what we can realize here immediately is, you see, if I develop such a Lagrangian mechanics for handling continuous systems, what stops me from going beyond, and instead of talking about just material systems, I can talk about abstract systems now. How about traffic? If you see on the road, you have traffic, there is a vehicle density and there is a flux flow, the flow of vehicles and so on. I can now apply all these ideas into abstract, and in fact, when you do that, this continuum mechanics and the dynamics behind it, the Lagrangian formulation of continuous systems, can be generalized to include more phenomena, and that is when we start calling it classical field theories. Of course, here the word classical necessarily means that it is not a quantum system. Okay. Classical, the word classical is used in many sense when you have relativistic mechanics and classical mechanics. Okay. Classical mechanics is non-relativistic mechanics, but that is not the sense in which we are using it here. For us, the classical necessarily means that it is not a quantum system. So, it could be relativistic system. And what kind of fields we can now talk about? How about gravity? See, gravity is a field which is not material particles. Remember, the field itself has an existence. The field is sourced from the material particles, but otherwise we are talking about field as an entity. So, you have this space, and at each point of the space you have this gravitational acceleration vector, okay, something like that. So, now once you do that, you can of course go over to electrostatics or magnetostatics, and then something that we of course we are always looking forward to is electromagnetism in its full glory. Okay. So, now what we want to do is probably we will not do that in this week, but look at the possibilities. Now, I can write down a Lagrangian for charged particles and the fields separately, so that they can be separately, you can obtain the Lorentz force equation from the particle and the field equations from the Lagrangian which pertains to the field part. So, now you can write down the Lagrangian for the entire system which contains charged particles and fields. Okay. So, something like that. So, I will give you few examples towards the end of this week as to how we write the Lagrangian for electromagnetism and charged particles together. Okay. Now, let us get back to the topic at hand. So, first thing I will do is I will start by generalizing or extending the particle Lagrangian mechanics to Lagrangian formulation for continuous systems. Let us do this in a very simple way. Let me start by looking at a long thin rod, so it is like a long rigid wire, okay, and its linear mass density is given by the quantity called mu. And what happens in this particular case? This of course we will assume that it is not a rigid rod, but its length can be changed by applying tension or applying force. So, when you apply force, the rod or wire will be stretched by small amount, okay, under application of some force there, and we will assume that this particular system obeys Hooke's law. So, this rod obeys Hooke's law, and Hooke's law says that the fractional extension that is delta L by L is proportional to the force, okay, and that constant of proportionality is Y, which is called as Young's modulus, named after the physicist Young. Okay. This is the system that I want to talk about. What things can happen in the system? You could of course have waves in this, okay, because it is extensible. You see, when I apply steady pressure, what I expect is that the change in the length of the wire will be linear along the wire. But if I, for example, look at possibilities where the elongation there is a elongation in one part, but compression in another part, we are talking about waves. Okay. So, there could be waves on this, fine. So, when I want to model this with a finite system, what I am going to do is model this with a spring mass system. So, think of it as a rod which has lots of these particles, okay, lots of these particles, and all these particles are connected to each other by springs. Okay. This is quite a okay model as long as you are talking about Hooke's regime. It is okay because you see, in a steady state, the neighboring ions or atoms in the solid would be interacting with each other through some potential. It of course is primarily electrostatic in nature. So, binding comes from the electrostatic potential. Now, if you remember the effective potential for 1 over r potential, then that has a small minimum, and that fixes the distance between the two atoms. And you can approximate this potential by small parabola around this minimum, and now the vibrations will be harmonic, and then this model will actually apply as is. Okay, fine. So, we are going to assume that there are n of these molecules or particles, each of them have a mass m, they are all connected by springs to or each particle is connected to its two neighbors by a spring, okay. And then the equilibrium distance between these two neighboring atoms, let us say, is a. So, what would be the total length of the rod? Total length of the rod will be n times a, and that is equal to L. Okay. And then we also want to match the mass density, remember. Okay. So, if you look at this chain, the density of this chain, when you calculate density, of course, you take the distances for calculation of. So, calculation of density would be as simply, you take certain amount of length, look at the mass inside it, divide by the length. And of course, when you are applying this formula, we are talking about distances which is probably large compared to the interatomic separation, which is A here, or intermass separation, which is A here. So, then finally, on an average, m by A should be equal to mu, and remember, mu is the equilibrium density. We are going to expect that these particles are going to move, and when they move around, then of course, the mass density would change. Okay. At least locally, the mass density would be changing. Okay. Now, what happens when I apply force? When I apply force, then each of these particles of course would move from its equilibrium position. So, now look at the model here. I am going to number them as ith particle, this is I plus 1th particle, this is I plus 2th particle, okay. And the equilibrium distance here from some arbitrary origin would be I A, okay. And then there will be I plus 1th atom will be at I plus 1 A. Then each one of them shift from their equilibrium position, and the amount of shift here, notice here, this is the shift in ith particle. I am going to write it as eta times I. Okay. Then I plus 1th particle probably has smaller one, I plus 2th particle has a displacement. So, this is eta basically is the displacement from the equilibrium position of the particle. Fine. So, this is the model that we have, and now what must happen? I must, you see, there is one more quantity to relate, the spring constant with the bulk property, which was Young's modulus. So, look at what happens here. If I apply the force at the end, okay, end of the chain. Then you have this n chains, n springs, and what is the effective spring constant that it would give? The effective spring constant would be k by n. What is the total elongation of the chain or of this rod? That would be the displacement of the rightmost particle minus the displacement of the initial particle, and of course plus n times a. Okay. Now, the force will be proportional to this. So, this is basically the total elongation multiplied by the force constant. And what do we want this equal to? Remember the fractional length. What is the fractional length there? This is nothing but delta L, remember, and this y by n times a, this is total length L. And now you compare the two sides there, and you can see that what must happen is value of k must be such that k times a must be equal to Young's modulus. Okay. So, this completes the parameters of the model. So, we have connected m with mu, then length with number of particles, and the spring constant with the Young's modulus. Okay. Now, let us look at what happens next. The position of the ith particle from some arbitrary, of course, the origin. I will say that at origin there is one particle which is 0th particle, and then there is the first particle at a, and so on. So, the position of ith particle, which I will write it as r I, that is nothing but the equilibrium distance I a plus the displacement from the equilibrium. Okay. This is the. Now, I want to write down the Lagrangian for this system. So, Lagrangian here would be simply L is equal to summation over all particles, that is what we want to do, summation over all particles half m times, remember it is r I dot square, that is velocity of the each particle or the speed of each particle. But remember r I dot is nothing but, so r I dot is nothing but eta I dot, okay. That is because I a is constant. So, r I dot square would be eta I dot square. So, that is what goes here, and plus or minus the summation of potential energies of each of those springs. Okay. So, for each spring, what is the net elongation? Net elongation would be r I plus 1 minus r I, that is the change distance between the two, and minus the equilibrium distance a. This is the elongation we are looking for. So, this is nothing but eta I plus 1 plus I plus 1 times a, that is your r I plus 1 minus eta I minus I a and minus a, and this is exactly equal to eta I plus 1 minus eta I. Okay. So, that is the elongation there. So, it is a k times elongation square. And this is the potential energy, this is the kinetic energy of each particle, that is the potential energy of each spring. Add it up to make the total Lagrangian. Okay. So, I will write it slightly differently, because I eventually want to make a connection with the uniform rod that we are talking about. So, I will take a out and then write this as m by a and write it as k a. This is going to become Young's modulus y later on, and then I have to compensate for that a as a square. Okay. Now, what is the equation of motion here? Equation of motion also can be calculated very easily. If I take d by dt of partial derivative of Lagrangian with respect to eta I dot and take one more time derivative here, then I will get eta I double dot, okay, and multiplied by there is a m by a, and the factor of 2 goes because you have eta I dot square. What do you get here when you take a derivative with respect to the derivative with respect to eta I? Remember, eta I will appear in two of these expressions. That means, you take ith particle, there are two springs on either sides, Okay. So, eta I actually appears in the summation twice. Take a derivative with respect to eta I and show that this will come out to be eta I plus 1 plus eta I minus 1 minus 2 times eta I. That is basically eta I plus 1 minus eta I and plus eta I minus 1 minus eta I. Okay, this is what it is. Fine. And then I want to take a continuum limit. How do I take this continuum limit? This is the trickiest part of the entire derivation. I want to take continuum limit so that there are infinitely many particles. Okay, so I am going to keep adding the particles to this. As I keep adding the particles to this, what I must do is I must keep the density constant. So, suppose I add more particles at a by 2. Okay. So, there is a particle added at a by 2, 3 a by 2 and so on. When I do that, mass will double. So, what must happen to the mass of each particle if I want to keep the density constant? I must actually divide the mass by 2. So, as I increase the number of particles, I must keep the total mass same, which means mass of the individual particles will go to 0. So, the limit n going to infinity, at the same time the spacing between the particles will go to 0. I must make sure that mass also goes to 0, mass of each particle, but as I take these two limits together, they are not independent limits. These limits are taken in such a way that m by a must go to mu, okay, or remain mu all the time. And at the same time, what happens to k? K must increase as the springs become smaller and smaller as n goes to infinity, and then I must do that in such a way that k into a must remain the Young's modulus. Okay. So, this is our limiting procedure. Okay. So, let us look at what happens to the Lagrangian. So, eventually now I have infinitely many particles. If I have infinitely many particles, then of course, I cannot index them with I as 1, 2, 3, 4. Okay. Once you take the limit to infinity, the system now becomes a continuous system. Once it is a continuous system, I need a continuous parameter to label all the displacements. So, instead of eta I am going to use eta x, where x itself is an index. Remember, x is not a generalized coordinate. What is the generalized coordinate here? That is eta, that is the displacement vector. Fine. X only serves as a replacement for I. So, in the discrete system, eta was a function from set of integers, that was discrete indexing, to let us say displacements which are real in number. Now, as you take, so this is for the discrete system. As you take a limit, now eta becomes a function which is some interval 0 to L, say, to R, and now this is a continuous interval. Okay. So, I need a continuous variable. I am going to use x because in the space the rod will be kept somewhere, and now I have a natural coordinate system which I can use for this rod, and of course, I will use one of these x, y, z for it. Fine. So, the discrete function eta I now becomes a continuous function, and that is when this is called as a field variable, okay, or a field. Fine. What happens to the Lagrangian? The Lagrangian will become, so there is the m by a, that is the mass density, this will become mu. Then eta I dot square, what would that become? All I have to do is replace I by x. So, it is a time derivative. So, eta now becomes not just function of this, eta of course is supposed to be function of t also. So, it is actually something like this. So, this would be derivative of eta with respect to time minus what will happen to K A? K A goes to y, and what is this? This is in fact nothing but the partial derivative of eta with respect to x. Remember, so you are taking two neighboring points. So, this is eta at x plus a, this is eta x, and when you take limit eta x plus a minus eta at x divided by a and limit a going to 0. That is nothing but the partial derivative of eta with respect to x. So, this will become partial derivative of eta with respect to x squared, fine. So, I will write that. So, now I will also replace summation by the integration because it is a continuous system. So, it is an integration over x half mu times eta dot square minus half times Young's modulus y times del eta by del x whole square. This is your net Lagrangian, okay, in the continuum system, for a continuum system. And remember, now of course, there are no particles, it is like a continuous system. So, this one here, this is called as Lagrangian density, okay. Remember, so there is a Lagrangian density and the total Lagrangian is obtained by integrating Lagrangian density over the space, okay. At each point of the space, there is a field variable eta associated with it. This idea we are going to carry over to almost everything. Look, we had particles, with particles we had energies, we had potential energies. Now, what is going to happen is, there is no individual particles left, there are only pieces which are delta x or delta v, like a volume in the space, and your material is sitting there. So, all we can talk about are the densities now. If you want total energy, you have to integrate over the system size in the space. If you want total potential energy, you have to integrate over this. But as far as individual points are concerned, what we will be talking about is the densities. So, we will talk about kinetic energy density, potential energy density, we will even talk about momentum density in few moments, okay? Fine. So, we have introduced this notion of Lagrangian density. Now, this Lagrangian density, from the Lagrangian density, I can get the equations of motion. The equations of motion also will generalize to the continuum system. What will happen? Remember, the Lagrange's equation of motion for each particle was m by a eta I double dot minus k a times eta I plus 1 plus eta I minus 1 minus 2 eta I divided by a square. This comes from, sorry, so I forgot to write equal to 0. Yeah. So, this comes from the Lagrange's equation for each particle. There are infinitely many equations like this. But when you go to continuum system, now what will happen? Your eta I double dot will become eta double dot at x. So, finally, I will write it as this is mu, this is second derivative of eta with respect to t square minus this is y, and what is this? If you remember the central difference formula for the second derivative, this is exactly that. So, this is second derivative of eta with respect to x. So, this is the equation of motion which we obtained from the finite system and take its limit to. And then the question that I of course want to ask is this. What I did was this, I took finite system Lagrangian and then took its limit here to give Lagrangian for the infinite system or continuous system. I took equation of motion for finite system and then took a limit for a continuous system. The question that I am going to ask is, what happened to my entire Lagrangian formulation or the machinery that I developed for Lagrangian? Can I now define or find a new procedure where, I can go from this continuous Lagrangian or Lagrangian for continuous system to the equation of motion for continuous system. I do not want to take the Lagrangian or a system, break it down into individual particles, finite in number, then write Lagrangian for each one of them, get equations of motion for finite system, and then write the equations of motion. No, we do not want to do that. We want to directly go from here to here. Okay. So, the Lagrangian for continuous system, I must use some equations which eventually will give me the equations of motion directly. That is the whole advantage of Lagrangian mechanics. You see, I can get the equations of motions directly from the Lagrangian. Fine. Now, there are few points that I will emphasize before I go forward. Here remember, the generalized coordinates are eta. They are the ones which show you the motion of individual particles or the particles which are sitting at x. So, eta of x and t, this is the generalized coordinate. What is x then? X is only an index, remember. X is just an index which is used to indicate individual particle, but the identity of the individual particles is taken out because there is a continuous description now. This eta is called as a field variable, okay, and we will continue to use this terminology now onwards. Instead of calling it as a generalized coordinate, we will call it as field variable. Okay. How many degrees of freedom in this system? Remember, at each point there was supposed to be a particle. So, now we have continuous system, there are infinitely many particles, there are infinitely many degrees of freedom in the system. This is the crucial part of the continuous system. The number of degrees of freedom are infinite, and the Lagrangian density that we define here, Lagrangian density is defined over what? So, remember, in case of finite systems or discrete systems, Lagrangian density Lagrangian is function of all the generalized coordinates and corresponding velocities. Okay. Now, what do we have? It is a function of all the generalized coordinates which become field variable. Remember, eta now is a function of x and t. So, x and t in fact can be thought of as two parameters of the system. So, you have derivative of eta with respect to x. So, your Lagrangian depends on this derivative, and Lagrangian also depends on the time derivative of the field variable, and then x and t will appear as individual. So, this is just like you had Lagrangian for finite system of y, y dot or q dot and t. So, now in addition to q dot, you also have partial derivative with respect to x and x as an independent parameter there. So, you now have all this. So, Lagrangian is actually defined as functions of all these variables, and in our usual formalism we treat all these variables as independent variables, okay, and the aim is to find a differential equation for function eta, and eventually when we get the solution, we get the solution which is this, which is finding eta. Okay. Now, so to find the procedure or the equations of motions from the Lagrangian, the best way to do this is to check whether Hamilton's principle holds or not. It turns out the Hamilton principle can be applied straight away here, and then we can obtain the equations of motion. Okay. So, let me start by writing down the action. Now, action is, remember, it is L dt. So, it is an integral of Lagrangian with respect to t, but the Lagrangian itself is an integral over x variable. So, I will write it as Lagrangian density. Remember, the two symbols, as long as the context is clear, should not be a problem. It is a simple L for Lagrangian and curly L for the Lagrangian density. Okay. All right. So, you have action which is all this. It is an integral of Lagrangian density with respect to x and t, and Lagrangian itself is function of eta field variable, eta dot, that is the time derivative. I am going to denote the space derivative by prime. So, this is eta prime is nothing but del x by del eta by del x, and then you have x and t. Okay. What we want to do? We want to find out that particular path. In this case, the description is not path, but description is a function. What is the domain of this? So, eta is basically function defined over a domain like this, okay, which is on this side I will plot x, on this side I will plot t. So, we are looking for a Lagrangian between x1 and x2, that probably could be length of your rod, and t1 and t2. Okay. And now, I want to find that eta xt for which the action is minimum. Let us do that. So, we want to find out the stationary function or stationary field eta such that delta I becomes 0. Calculate this. The entire derivation of course will proceed exactly along the lines of the discrete case. All that we have done is a particular function has been replaced. It was a q which was supposed to be only function of t in case of the particle dynamics. Now, it is function of x and t. Okay. So, delta I can be calculated by varying eta, remember. So, I am going to assume that the variation in eta, so delta eta is the variation in eta. Okay. So, you have a function which is defined over this rectangular patch which I have shown here over this, and then this function is tiny bit modified, so that on the boundary or perimeter, on the perimeter the value of the function must go to 0. Okay. So, eta delta eta is of course 0 on the perimeter, or at x is equal to x1, at x is equal to x2, at t is equal to t1, at t is equal to t2. At all these 4 boundaries, your variation must be 0. Okay. So, now you take it is a derivative of this or variation of this with respect to eta. So, this will be partial of Lagrangian density with respect to eta into delta eta plus partial of Lagrangian density with respect to eta dot into delta eta dot. Okay. Remember, what is delta eta dot? It is nothing but d by dt of delta eta, and same thing for the partial derivative with respect to x. And what did we do in case of particle dynamics? Integrate this by parts. If you integrate this by parts, you get surface term and you get the integral. Okay. Surface term will be 0 because delta eta is 0 on the boundary. So, all that machinery, if you remember, will apply as is here, and then I will probably be able to write down the final answer directly without going through the intermediate steps. Remember, there will be a surface term which becomes 0 here. So, basically d by dt which appears in the delta. So, this will be d by dt of delta eta, which will get transferred to partial of L with respect to eta dot, and then delta eta can be taken common outside the entire bracket. And now you have this bracket inside multiplied by delta eta. Remember, delta eta is also function of x and t, and what must happen for stationary condition? Delta I must be equal to 0 for all possible delta etas, and we know what happens then. That means the integrand here which multiplies delta eta, that itself must be 0, and that gives me the final equation there. So, this is your equation of motion. If I apply it to my previous problem of the rod, I should get, so if I put in place of Lagrangian density the Lagrangian density for the rod, then I should get the equation of motion for the rod. And let us do that. It is a very simple example. So, your Lagrangian density for the rod is mu times eta dot square minus y times eta prime square. Now, here when you take a derivative with respect to eta dot, I will get 2 times eta dot here, and that 2 cancels with this, and I take one more time derivative, I get eta double dot. That is exactly what you have here. What about this term here? This one does not have eta dot, so it will not contribute to this. This term contributes to only the second part of this equation, and that is d by dx of del L over eta prime. What is eta prime? That is a partial derivative of eta with respect to x. So, what will that give you? It just gives you 2 times eta prime, and take one more derivative with respect to x, that is eta double prime, and eta double prime is nothing but second derivative of eta with respect to x, and that is equal to 0. There you go. So, the earlier we saw that if I take a finite system, take continuum limit, I get a Lagrangian. If I take equations of motion for finite system, take a limit, I get the equation of motion for continuous case. And here we show that if I use the Hamilton's principle, then I actually can get equations of motion. So, your Lagrange's equations for continuous system are given by this equation here, okay, this differential equation here. Fine. And remember, this is just one differential equation, but like every other differential equation, it is a point differential equation. For each x, it is like you can think of it as each x there is one equation. So, there are infinitely many equations because there are infinitely many degrees of freedom there. Fine. So, what kind of generalizations we can do with this now? The first generalization is, I took the wire and I took only longitudinal displacements. How about taking displacements along the other directions? So, the first generalization I will make is you stay with the rod, but add the transverse displacements too. So, now a displacement vector can be some vector like this. Okay. So, this is eta vector, and I will write this eta vector as comprising of 3 components. Typically, I would of course like to use the same coordinate system for the displacement which I am using for the rod. So, if I were using x here, I would use probably the same x for noting the displacement of the eta, displacement of the particle. But that is not a compulsion. You see, x is only a label. We are assigning a vector at x. Why should I use the same coordinate system for eta? There is no need. You can actually use whichever coordinate system you want for eta. And for that, I will in fact write eta as a vector, but as eta 1, eta 2, eta 3 probably, something like that, right. So, then what will happen? It is a 3 component field or a vector field. Okay. It will become a vector field if it acquires the properties under rotation. But in this case, of course, the space is only one dimensional. So, such a thing actually does not come here. So, this will be simply 3 component field here, because it has 3 components. And then what would be Lagrangian density? Now, Lagrangian density depends on how many arguments. It depends on each of these field variables, each component of the field variable, then time derivative of each component, then space derivative of each component, and then the 2 parameters x and t. How many total arguments are there? That is 3 here, 3, that is 9 plus 2, there would be 11 such arguments for your Lagrangian density. Okay. To make things easier, now I am going to change the coordinate, change the notation. You can immediately see that this is going to get really messy in the sense Typically, I will also generalize this to 3-dimensional space. So, total number of parameters would be x, y, z and t. Those are indices in some sense. And then the field itself has 3 components. Writing the whole thing down would be a mess if you want to use x, y, z or eta 1, eta 2, eta 3. So, what I am going to do is we will develop a new numbering system, naming system, okay, notation. So, I will call t by letter x 0 and x as x 1. Okay. So, when I take a derivative of eta sigma, remember now already eta is being numbered, the components are numbered as 1, 2, 3. So, here sigma can become 1, 2, 3 depending on your coordinate system. Now, when you take a derivative with respect to t, that is same as partial derivative of eta sigma with respect to x 0. Remember x 0 is our new notation for t, and compactly I will write it as eta sigma, put a comma and put 0 there. This means I have taken the partial derivative of eta sigma with respect to x 0. What about partial derivative of eta sigma with respect to x? That of course will now become eta sigma comma 1. Okay, fine. Now, see what happens. Now, I can write this as L, which is function of n sigma. Remember, sigma takes values from 1, 2, 3. Then all possible derivatives of n sigma comma mu. So, now this means sigma will vary from 1 to 3, mu will vary from 0 to 1. How many total entities are there in this? There are 6, there are 3 here, and I will write x and t together as x mu. So, mu here takes values 0 and 1. So, how many are there? 2 more. That is total of 11 coordinates there, okay, or 11 variables. Instead of variables, I probably should use the word arguments, 11 arguments. And then you write the action in this new notation. The action will be L dx mu. Now, this symbol here in the bracket dx mu is actually product. So, this is dx 0 dx 1, which is same as dt dx. Okay, fine. So, now I will write down the Hamilton's principle in the new notation. So, the action like this is minimum for that eta which satisfies this differential equation, and that is, now you see, I will quickly go back to the previous slide, and if you remember here. So, what you have is there are 2 terms here. One is d by dt del L over del eta dot, and then there is a d by dx of del L over del eta prime. What will that become in this case? So, here let me write this, it was d by dt of del L over del eta dot and plus d by dx of del L over del eta prime. Okay. In our notation, this is d by d of x 0 plus del L over del, what is eta dot? Eta dot is nothing but with respect to, so here of course we do not have sigma. So, I will just leave it as sigma takes only one value for my rod case, 0 plus d by dx 1 of del eta sigma comma 1. You see, there is basically these 2 terms are identical except for the change in the index there. So, I will write it as d by dx mu partial derivative of L with respect to eta sigma comma mu, and then sum over mu minus del L over del sigma. And how many such equations you would get? You will get as many equations as the number of components in the system in the field variable. So, here the field variable has 3 components. For each component you will get one equation there. Okay. Fine. Now, the second generalization of course is taking it to 3 dimensional case. Now, take this case where you have a bulk solid. So, solid has an extension not just along one line, but it extends in y direction and z direction too. And then I have x, y, z and t as 4 parameters. At each point there is a displacement vector. These 4 variables together, I will write them as x0, x1, x2 and x3 to make it into a 4 dimensional abstract space. And then write Lagrangian, which is function of field variables, their partial derivatives and the parameters. Okay. How many? There are 19 arguments there. Look, there are 3 of this here, there are 3 into 4, that is 12 here, and then there are 4 here. Okay. So, there are a total of 19 arguments there. How would the equation of motion look like? Equation of motion just looks exactly same, except what is to be remembered is that mu here now, instead of going from 0 and 1 in like in our rod case, mu goes from 0 to 3. Okay. So, this includes partial derivative with respect to x, y, z and t, everything there, and there are again 3 such equations there. So, this is the generalization to the entire bulk system. This is what the continuum mechanics program would be. Now, even though I have constructed that 4 dimensional space here, remember there is no relativistic, this is not same as the relativistic 4 dimensional space which we call as Minkowski space. No, there is no such requirement between x and t. Remember, as far as the notation is concerned, can you see that in fact in this too x and t are treated exactly on the same footing. Even though they are treated on the same footing, you see I have not actually specified whether if I change the coordinate frame to another frame which is moving with uniform velocity with the first one, which kind of invariance will apply. Here for the continuum mechanics, I am going to still assume that your Galilean invariance works. If you want to construct a relativistic field theory, then of course we will have to think of this as a Minkowski vector space. But to begin with, in this description as such, there is no such transformation property built into it. Okay. Whenever we are talking about electromagnetism, I actually would like to build that property into this. So, that also will become a main consideration in the Lagrangian. Okay. Remember, when we go to the fields, in fact that the reason, one of the biggest reason for taking this Lagrangian dynamics to various field theories including to quantum mechanics and quantum field theories is when you are looking for theories of the nature, symmetry plays an important role. In fact, many times you make your guesswork or hypothesis for the Lagrangian of the entire universe based purely on the symmetry considerations. Okay. This is built into this entire formalism there. Okay. Finally, I will do one simple example, say sound waves. So, for the sound waves in air, I will of course not derive the Lagrangian. I am just going to take a Lagrangian and derive the equations of motions from there. The Lagrangian can be derived by looking at the interactions between the individual molecules there. Okay. They of course happen in the form of collisions. So, if you put all that together and if you think of eta as displacement of gas molecules from its original or equilibrium position. So, in its 3 component vector field, I will still use the same x, y, z as the coordinate system, and then the Lagrangian can be written as this is mu naught times eta dot square. Here mu naught of course is the density of the gas, then 2 times P naught times divergence of eta. Okay. What is divergence of eta? It is a partial derivative of x with respect partial derivative of eta x with respect to x plus y component and plus z component. And then here of course P naught is the equilibrium pressure, gamma is the ratio of specific heats, and into divergence of eta whole square. This is the Lagrangian density for the motion in the air, okay, motion of the particles in the air. Now, if I want to write this in terms of our notation, then remember this is also another convention which is quite commonly followed in the books. If I am using index I, which is Latin index, this goes from 1, 2 and 3. If I use the Greek one, then that goes from 0, 1, 2, 3. Okay. So, here when I write eta vector, I actually mean eta I, which means eta 1, eta 2, eta 3. So, and same for the gradient there. So, this one will become mu naught times eta I 0, eta I 0. Necessarily there are 3 derivatives in it. You see, why did I repeat this instead of writing it as eta I 0 square, is because I want this expression to be eta I 0, which is actually equal to del of eta x by del t whole square plus del of eta y by del t whole square and plus the z term. Okay. So, there is an implicit summation in this term. I repeats in 2 terms, and that is why I will sum over I. So, this is in fact same as summation over I going from 1 to 3. Here this is eta I, again the 3 terms in this, and then there is eta II, eta JJ. Remember, I again goes from 1 to 3. So, there is a summation. There are how many terms in this? There are 9 terms in this, remember. Okay, fine. Now, calculate the equation of motion. I will do it only for one case, that is I is equal to 1. So, take only the first component of the displacement or the field variable, that is eta 1, and write the equation for eta 1. So, for eta 1 it will be mu naught times the second derivative of eta 1 with respect to t, then multiplied by minus gamma times p times. It will turn out that the middle term actually does not contribute, gamma times p naught times d by dx of. So, if you take the derivatives, I will of course ask you people to do this. You see, initially to get used to this particular numbering scheme and this notation, you need to do this, you need to practice this often. So, sit down, write down all the terms from here, take its appropriate derivatives and take this equation out. And this of course again simplifies too, because there is a d by dx here, and all these terms I can write it in the vector form again. But the typically sound waves in the air, they are not written in the wave equation, does not look like this. In fact, the wave equation is in terms of density. So, if I for example want to write it in terms of density, then I will add this new variable here, which is called as density rho, which is minus of gradient of eta. Okay. And then if I put that here and take a, so this is your final equation, take one more divergence of this equation, you get this here. So, this divergence operator will commute with the time operator or the time derivative, and divergence operator here operating on dot will give you del square here, and then this particular del dot eta, you replace it by rho, there you go. That is the equation of motion for the sound waves. And what is the velocity? Oh, this looks like a standard wave equation. Velocity will be given by, sorry. So, the velocity will be equal to, so it will be square root of gamma p naught by mu naught. Then fine. So, this is how the Lagrangian formulation works for the continuous medium. In the next lecture, I will talk about stress energy tensor, which is also similar to what we study in elasticity. Okay. And of course, we are talking about continuum mechanics, that also becomes one of the main considerations here.